This meeting is being recorded.
And we have a new voice.
Okay, William.
All right. So basically, today I'm covering 3 different papers. 2 of them are fairly similar. BoxtoCortex and TopOFit have similar methods for surface reconstruction. Deep CSR uses a slightly older method, I would say, which requires topological processing that slows it down significantly. I'm primarily interested in the first 2 papers, but almost every paper on surface reconstruction I've read cites deep CSR, so I wanted to include it. The first paper is BoxtoCortex, fast explicit reconstruction of cortical surfaces from 3D MRI scans with geometric deep neural networks. Okay, so their contributions, the authors ensure spherical topology of the generated meshes by learning to deform a template mesh with fixed topology and arbitrary resolution. BoxtoCortex models the interdependency between white matter and field surfaces by exchanging information between them. They propose a new loss function for training explicit reconstruction methods that leverage local curvature and to weight camphor distances, and they demonstrate BoxtoCortex as an improvement over other methods. So just to kind of like give you a primer on their like what you see in surface reconstruction. You the top values are BoxtoCortex, and the bottom values are involve marching cubes. So like the deep CSR method and FreeSurfer and some other methods, they all require this marching cubes, which creates these artifacts, which like stair steps or staircases. And while deep CSR can kind of get arbitrarily high resolutions and make this less of a problem, it still like seems to be a little bit of a problem, and it's interesting that there's an alternative that doesn't result in these.
Quick question, since marching cubes can only work on segmented brain imaging, do they apply segmentation as well for their method, BoxtoCortex, or it's
segmentation is part of their pipeline. It's like there's a CNN that does segmentation, and then a GNN that does that is their surface reconstruction. But they don't do marching cubes. The GNN skips that stuff.
Yeah, but they do segmentation, so it's not like give it the T1 and it's not like end-to-end. There is a intermediate step.
I think it'll be clear by the end of this.
Okay.
So BoxtoCortex background. So basically, this is kind of like I mean, I would almost say this is like generations, but it's probably wrong. But these require topology correction and surface extraction, which basically implies marching cubes, these 2 methods. So you'll see a CNN followed by topology correction and surface extraction, or a CNN with a fully connected network with topology correction and surface extraction. The new method adds a GNN, and basically that allows them to skip topology correction, which is like one of the reasons FreeSurfer is so time consuming. So basically, anybody that's using topology correction isn't really beating FreeSurfer all that much on time, I would imagine.
So could we just add like a task of surface generation to MeshNet, and it would be pretty much equivalent to one of these models at least?
Yeah.
I don't know, to Segrecon, I would think.
Yeah, that was the idea initially, but what are the top 2 figures? Those CNNs and CNN plus FCN, are they doing segmentation?
Well, I think this is segmentation occurs here, and then they use like they extract the topology from the segmentation with and then use marching cubes.
Yeah, so this is the regular FreeSurfer approach. Only the segmentation is replaced with deep learning.
Yeah, that sounds right.
And FreeSurfer does that too. Yeah.
Yeah, FreeSurfer does that. has some marching cubes. And it mentions that right here. Segrecon's another one.
So how do they define the surfaces?
Usually assigned distance functions. So like deep implicit representations use assigned distance, assigned density functions. I think they also use occupancy grids. So this might use occupancy grids, I think, because it's doing segmentation. But in the same vein, I kind of go into this a little bit later. Like there's different ways of defining ISO services, and you can kind of use occupancy grids or occupancy functions, or you can use sign distance functions. And like basically everywhere that's zero in a sign distance function is like the same thing as an occupancy grid, but I'll reiterate that later. Okay. That's the sign distance function basically is a continuous function. So they're able to kind of like make their marching cubes finer and get better, get rid of those stair-step artifacts that I mentioned earlier. Yeah. So basically these two methods are slow. This one's faster. And that's kind of the whole motivation in the first place, is to speed up the pipeline. So, all right. So mesh-based service reconstruction is the third one. And it basically, there's an iterative, the whole network predicts a deformation values for each vertex that's in the mesh that's being deformed. So in this paper, I think they deform the mesh 4 times. So the final layer of the network basically is predicting a like all of the deformation information for the mesh.
It's very similar to the other paper that you presented, right?
Yeah, the cortical flow. I mean, like it seems like they're doing the same thing. But cortical flow creates this field with like a neural ordinary differential equations or something like that. Some sort of differential equations are involved in them deforming the mesh. I think they create like an entire space that, like if you ask where does this point need to go, it tells you where it needs to go. Whereas here they tell you per vertex.
So 300,000 vertices per hemisphere, right? About that's the resolution.
Yeah.
How they handle that? Are they? Is it like?
What type of deformation are they doing? Is it just
I think they did. I remember. I didn't go too much into how they get into their like highest resolution results, but I think they do some like low resolution results and then upsample or something like this. But I kind of left that out of the presentation because I was doing 3 papers.
what type of deformation do they do? Nonlinear or linear transformation? Because it's doing 4, so I was wondering like what they are.
I get into the architecture a little bit later. All right, so basically now, this should basically be 3 or 4 slides. So this is a pretty big image. Split it up into an overview and then like the top half and the bottom half. The top half is basically performing image segmentation using a UNet style architecture. All of these are like this kind of, I guess you call them skip connections of the UNet, or the parts that connect the similar pieces in the encoder decoder portions. They create this segmentation map.
Brain mask, right?
These are the features. So that's important to remember that all these features in the feature. So the top half is CNN doing segmentation. The bottom half incorporates more information about where the current mesh is from the previous step, and takes these features and uses that to tell where all the vertexes need to deform. So basically, just to reiterate in a little bit more detail, there's like they say a residual UNet architecture performance image feature extraction. This encoder decoder FCNN solely takes the 3D brain scan as input and segments it into brain and background voxels. So as I think we've already established.
By brain, do they just define gray matter or?
I don't really know. I know that their output is white and peel. I don't know, and their input is an MRI. So I don't know what happens here really.
Okay, it looks like they do, I think, both white and gray. So it's probably the peel surface, yeah.
All right, the bottom half of that architecture pipeline is here, and the GNN takes a template mesh as input. There's 4 deformation steps, so they start probably from a sphere, and then are either that or an average, and I can't remember which, and deform it 4 times to get the final result.
How?
So the final block, I mean, it'll, how?
Like what type of deformations? Do they do it on each single vertex?
Yeah, so each vertex has to be told where to move, and the output of this final stage is
Okay.
like they call it phi or whatever, but it's basically like per vertex. Here, it's actually says it here. Each deformation step predicts vertex specific displacement vectors relative to the mesh produced by the previous step.
And they use a graph neural network, it seems like.
I think that's what GNN stands for. I mean, like at the beginning of the paper, it says like geometric something, but everywhere
Well,
else.
what is the graph then? The mesh that connects?
Yeah, I
the
think so.
vertices?
Yeah,
That's also my,
yes.
that's also, because I was thinking, it makes way more sense because otherwise you're not sharing anyways. Like if you don't do.
Yeah, I mean,
graph for those
300,000
vertices for the mesh, then it'll be like, you have an insane number of parameters just for these 4 steps.
Yeah.
Right, and so I do get into like the equation for the GNN later, so.
Because if you do it for each hemisphere, you get 365 times, like, times 4 essentially already just from this. And then
Where are you taking the numbers? I'm not tracking.
365 is like the number of 365,000 is like the number of vertices in a hemisphere in FreeSurfer.
Oh, I thought around 300. That's what I remember, but you know exactly.
I know the exact number because I had to work with it, so I had to like look at the shape.
But then 3 parameters per each, right? X,
Yeah.
Y, Z,
At least,
vectors, where to move.
Yeah, at least, and that's not even doing a lot of nonlinear stuff, because if you imagine only 3 weights and then some nonlinearities, that's.
Oh, non-linear is fine. With 3 weights, you just point where
Right.
this point is moving.
No, true, but it's
Non-linear-
completely, so you assume that it's a linear transformation.
No. Transformation could be any transformation. You're just saying the point currently is here, move there.
But it's learning a linear, the gradients are linear, right? Because there's no nonlinearity. It's just 3 weights.
No, it's a GNN. It's non-linear transformation.
No, so yeah, that's what I'm saying.
It spits
Because
out
it's-
a vector.
No, because it's a GNN, yes, but I'm saying like if you were just like parameterized each voxel, then you would have gotten the.
Not the voxel, right? They're parameterizing each vertex.
Yeah, I guess it's like just in the mesh.
Yeah, it must be on the mesh. Okay, cool.
This is basically only just details about the architecture that I feel familiar, like Bash Norm, Relu. And also reiterating that there is a per vertex vector for each deformation step. So like each vertex is told which way to deform at the end. So this is probably where, if you're familiar with graph neural networks, you'd either be able to determine whether it's the same or different, but like it looks like that's kind of cool notation. If you're familiar with graph notation, it should be not too bad. This is like the neighborhood of vertex I, and so basically the feature vector for vertex I, when it's updated, is going to be proportional to like the cardinality of the neighborhood, and like these are like the learned weights and biases, but this second summation is basically where the feature sharing occurs. So like you aggregate information from your neighbors here. Is that clear?
Is there a non-linearity on it or not? Is that really right?
I think it mentions it right here. So besides the mesh output layers, the graph convolutional layers are followed by batch norm and ReLU layers in our network. So it's not all that, it doesn't strike me all that different than any of the other neural networks we've seen before, except for that there's this like aggregation stuff. It's like just a free definition of what it means to be a convolution, I guess. But the downstream flow is not all that different. Okay. So this is where I start getting into the loss functions. So there's basically two loss functions. Like if you recall back to the CNN and the GNN, this is probably a loss that's more impactful on the CNN because it pertains to the segmentation maps, and this is a loss that's more impactful from that, but the GNN, the mesh deformation. So this is like the predicted mesh in the ground truth, and they get their ground truths from FreeSurfer. So unfortunately, it's still supervised and requires FreeSurfer to produce the supervised data.
And it's just for training.
For training. So it's not doing anything unfamiliar to supervised learning. Okay, so the voxel loss, this is pretty straightforward. It's like binary cross entropy loss between like the predicted values 0 or 1. So like 0 for black and 1 for white, or vice versa.
Wait, so they have two losses, one for segmentation and one for the mesh?
Well, I mean, they have one loss with two terms.
Oh, okay, good. I was staring at it.
And they further break down these terms going forward. So as I said, a binary cross entropy loss for segmentation. And let's see, the mesh loss is their mesh loss includes regularization, Laplace smoothing, and geometric consistency, which I will go into more later. I don't go into Laplacian smoothing all that much, but there's this term contributes to making sure there's no sharp edges. This is a more like a brute force comparison of a point cloud against another point cloud.
How do these two networks interact with each other? Because I don't see why you wouldn't just train them separately.
That's a good question.
Through the loss.
So I would say that they interact with each other here. So these are the feature maps at each stage. And these get concatenated into the input of each stage of the GNN.
Wait, then I don't get it. So it's GNN.
GNN is looking at the features from the CNN and the meshes from the previous deformation.
Yeah, that actually makes a lot of sense.
It doesn't, to me, mechanically, it doesn't make sense because the deformations are volumetric, right? They're like 3D or depending on how they did. Volumes of low resolution, less than 256 by 256. And you have okay, features F1, F2 is a channel in the CNN, I guess.
Yeah.
And then what GNN is just message passing on the graph. So are you like the nodes have geometrical location on the graph, the vertices, but those feature maps, you don't know how those nodes correspond to those feature maps. Who you feed it to, like every time, everything for every vertex. Like this is unclear, but it's
Yeah,
okay.
that's
But yeah, there is an exchange, not only through the loss. Yeah, but
Just trying to see if it's obvious from this.
no. Oh, actually, can you go back? It's just looks like a standard. Well, F is that feature, or F is what?
FJ is the other feature to the neighbors.
Yeah, it's just the neighbors. It's just a simple GNN. They don't show how they feed those other features.
That's a good point. I don't really know how they, I mean, it says concatenate, but
Well, I mean, but to what geometries are not compatible yet, and we need to project and blah blah blah. All of that.
yeah. Well, that's something I definitely want to find out when I get into the code, but I figured I could get to the presentation without knowing it, I guess. Sorry. Where would it be? Okay, so the loss, the geometric consistency. So I guess going back one slide. So the mesh loss has a regularization term which deals with smoothing, and geometric consistency loss, which compares point clouds that are sampled from the triangular meshes. Okay, so this doesn't go into it very much. This just declares that it's a chamfer loss. Chamfer loss usually compares minimum values against minimum values, either typo fit or this has an optimism, or may probably both have an optimization on it. So where like chamfer losses is kind of inefficient because it compares, like has to look at like in square points or something like that. But because they map onto a template mesh at the beginning, they're able to know to only look at neighbors, I think. And when looking for like correspondence between points.
Also, they call it mesh, but it must be just a point cloud, right? How is mesh represented? Just XYZ for each vertex, or like triangles too? How
It seems like also that distance function, the sine distance function, right? Or not?
the chamfer loss, or which one?
Like in the beginning, they were talking about the sine distance function.
Oh, that's for a different approach. The
Oh.
implicit representation.
Yeah, so this is something I definitely want to look at in the code, is like how they sample from this triangular mesh in a differential way in order to compute the chamfer loss, but they claim to be able to do it. And also there's this curvature term which I don't fully understand, but it seems to have a hyperparameter, be a hyperparameter of some kind maybe.
I think normally the way they sample is they pick a point, like a random point, and then you say like, for example, I want 100 samples. What they do is they pick a point, and then they pick the furthest point from that point, and then the furthest from those 2 points, etc.
Yeah, and they also said the sampling strategy that you use
For this
dramatically
point.
affects the quality of these meshes. So I don't really know how they do it, and that they say that it's important that you do it well. This curvature, as you'll see in some of the results, that term dramatically affects the quality of the meshes, being able to capture the fine ridges of the brain. So this is not just a standard chamfer loss. This has a term that weights curvature. So here you can see, so this is with like one of their values of the curvature being one value versus another. This is with it not existing, and this is FreeSurfer, I think, white. Yeah. So you can see that the curvature loss matters. This is a comparison with FreeSurfer. The results look pretty good to me. That's not very highly quantified, but I left the tables out of these presentations because I just find it frustrating to go into tables. It takes a lot of time. And it's not worth it, at least for the sake of presentations. So you can see here that the FreeSurfer that actually fails in a lot of situations. So pink is FreeSurfer, and FreeSurfer like goes out of its boundaries in many different scenarios. They define like what the scenarios tend to be in the paper a little bit more. I don't remember what they are, but their method, at least in the examples that they cherry pick, fits pretty well as far as I can tell. These are peel surfaces. So this shows you topology errors for some of the people that they compare against, which is the third paper in the series, which is Deep CSR. Deep CSR, this is before topology correction. So there's like some topology errors that they show. And after topology correction, because it's not really aware what it's not aware of the brain structures, tends to make artifacts that are even worse in some scenarios. This is FreeSurfer ground truth. So FreeSurfer is doing good in this case. But it's just, I think they're just reiterating that topology correction is both time consuming and it doesn't really do the job. So being able to remove that from the pipeline is ideal. The cortical thickness comparison shows that they're able to like capture the thickness of the brain sufficiently. Next,
How do they measure that?
I mean, it looks like millimeters, but I don't remember.
No, I mean comparison, ground truth, manual segmentation, or?
I think they're comparing against FreeSurfer. So it's good.
Right.
The manual is not available. I mean, it's so tedious. There are like 6 brains, or I don't remember exact number, that locked in a safe in Massachusetts General Hospital that were manually segmented.
No, but yeah, but so that's I mean, I think I've read a few of these papers, but I always feel like it's kind of weird to be like, oh yeah, FreeSurfer's not that good, so we're doing a new thing and we're going to compare it to FreeSurfer as a ground truth. Like it feels like that's like circular reasoning.
Yeah, we couldn't come up with any better. We thought about it.
Right. No, I understand it's hard.
Well,
I'm not saying that.
FreeSurfer takes time. You have to manually go through it. Every subject might take up to 30 minutes or
No,
1
I know.
hour.
I mean, it
to
takes
find
like
it.
24 hours to do the MRI recon orbital thing.
Yeah,
I'm
about
gonna
8
have to
now.
kind of
Looking for like a
compare this
manual
to the model
segmentation
to-
would take
for
even
the sake
longer.
of-
No, sure.
Yeah.
We did sometimes do that in my previous lab.
Yeah,
To compare.
take like up to a week per volume, probably at least.
Yeah, I think what that's kind of saying is that even saving time is already better. If it's
No, I
just
know,
the
but it's
time.
kind of hard to say if like it actually is better than FreeSurfer. Like they're doing all these like, because if FreeSurfer is making mistakes and you're saying, oh, we're doing it better than FreeSurfer based on a mistake that FreeSurfer made, that is, it's not doing better. It's just doing the same thing worse. Like I don't really,
But is it doing it like without the FreeSurfer mistake?
well, that's the question, right? It's very hard if you don't have a ground truth of the actual.
Well, the ground truth, it is, I don't know how the pipeline is that you run by FreeSurfer. Every subject gets up to 24 hours. Then you go through FreeSurfer data for each subject and look at for defects because it is a visual
No,
thing.
I
and
know
you
how
can
it
look-
works. I've done this like myself, but like my point is, I know how FreeSurfer works, but there's a lot of mistakes in FreeSurfer. That's the part of the point of the paper. I mean, I understand that like going faster is really important. That's why FastSurfer and stuff started. But still, they're also doing quantitative comparison of how good their segment, like their stuff is, even though they know that there's issues with the FreeSurfer one. So it's kind of like saying, oh, I'm using ImageNet, but half the labels are incorrect, but I'm getting 100% accuracy. It's like, well, but isn't that not?
You don't know
I
how
think what
incorrect you are.
What
No,
Oshkosh
that's
is
what I'm
saying
saying.
is we usually don't have unvetted FreeSurfer, right? You don't just run FreeSurfer and say, this is my final output. End of the day,
No,
right?
that's
You go
true,
through it
but
manually.
there's still often mistakes in FreeSurfer, especially in the sort of reconstruction.
But
It's
you
been
will
hard to
check it.
check them in the patch.
Yeah, that's what I'm saying. I understand that most of the big ones are out there, but my point is more like still there's issues oftentimes with FreeSurfer, even if you check them.
Well, here's a statement that I would market it is a tool that is much faster than FreeSurfer and is no worse than it in quality.
Right, but that's why I didn't understand the quantitative comparison.
Oh, well, you at least need to show that it's no worse than FreeSurfer.
No, that is,
or
okay, that's
FreeSurfer.
fair, but like,
You can show that it's better because you don't have.
right.
Until you have a ground truth, yeah.
The top of it portion of this presentation, honestly, this paper, I mean, it was so similar to BoxtoCortex that the main reason I put it in here is because I'm actually, that we're working with a group that did this.
You're saying it's kind of like very similar architecture, the same architecture and everything?
I mean, they use different loss terms in some places. It's worth talking about, but we can get through this a little bit faster, probably. Hopefully by the end of this, one of the two or both will make sense.
Oh, you're trying to get it running, right? The goal is. to
Yeah,
have
this is the first one
tools.
I'm getting running, and I've gotten this one to run, but I need to like have better display of the prediction versus ground truth, but I can get the prediction.
Yeah, we're collaborating with the authors. on
Yeah.
this one.
Yeah, but the BoxtoCortex paper is much more self-contained in the amount of background it provides you and the amount of descriptions it provides, but the architectures are similar.
Maybe it's a difference with journal and conference, I don't know. Is it-
I don't know.
Yeah.
So there's not a whole lot of detail here about their architecture, other than the fact that it's a CNN that that interfaces with the GNN or GCN and produces a deformation field, and there's multiple deformation steps, which is something we've already seen before. This
It's
is
like
five-
everyone is doing that, even Cortical flow, right?
Yeah.
It's kind of. the
Yeah,
same.
I think, like I said, I think the difference is that the GCNs predicts per vertex which direction each vertex could flow. So it's like a discrete set of discrete, like R cube values times number of vertices. But like cortical flow, I think it actually like takes like the three-dimensional space of the MRI and says like if you're at this space in the MRI, you go that direction. So it creates like a vector field for the whole space. I could be wrong about that because that was a hard paper and I didn't fully understand it. But if there's a part 2 of this, I'm going to go over a paper that's very similar to that again, but I'm not sure if there's going to be a part 2 or not.
So what is the signal for CNN here in the picture? It's not segmenting anymore, right? Or because the only thing is the loss, there is no segmentation, or is there segmentation?
You know, I don't know, but I mean, like when I can't remember off the top of my head. I think there must be because they like in this. I skipped this slide, but they say the traditional pipeline is white matter segmentation, followed by surface reconstruction. But it probably says in the paper, but I didn't go into significant depth on this because I went into more depth previously on the other one. Anyway,
What is sampling? Are you going to talk about sampling spatial image features?
I think that's I think that's similar to the like that's the whole purpose of the CNN is to get these image features out. But
Yeah, but what sampling is like some random selection. What are they doing there?
I don't know. So the objective type of fit objective function. So basically they're minimizing the distance between the sample point clouds, and they also have a regularization term to increase the smoothness of the meshes. Let's see if there's anything important here. We've seen like basically their networks predict the deformation field per vertex template surface. So they map the ground truth messages into like an average so that they can compare meshes efficiently, like I mentioned earlier. They do graph convolutions at several scales and in order to create higher resolution meshes. Yeah. So this is just reiterating that that the mapping into a common template allows them to efficiently like find correspondence between ground truth and prediction meshes. And this is a Cantor loss again, but it doesn't have a smooth a curvature term, so that probably would improve the results a little bit. And they also have this term, which the previous paper didn't have. I like this term just because, like, once you play with meshes for a little while, like the triangular faces, like you can have like the high level mesh look kind of similar, but like if you don't have the triangles angled in the correct way, it'll be like really messy. It'll have like a lot of jagged spikes in areas and whatnot. So this like enforcing that normals of the faces are consistent between prediction and ground truth seems reasonable to me.
I mean, in terms of that, this function and the kappa that they left out, I'm just thinking, why can't we model it as a like a physical process? There is a surface that has thickness and viscosity, and then you won't have those small features because it's thick. It's like if there is some viscosity to it, or like it just you know, it's a stiff surface, you can't bend it more than possible. You can't create tiny features either. And if we can introduce these properties into the, like, because you're deforming. So if you're deforming with infinitely bendable surface, of course, you're getting those, like you had this example of bridges. But if it's not infinitely bendable, if it's stiff, then to some degree, you can control how smooth it can be. It just, you know.
Yeah, it seems like that. All right. Okay. So there's like this sentence here kind of comes to mind. The metric encourages smoothness without shrinking the mesh towards the center of mass. Side effect present when using voxel-based spring terms. So this encourages like a certain shape, but like there's a tendency to like either like become too flat or become too rigid or too pointy, and this kind of produces it without having to have a hyperparameter, I think. But implementation UNet shows up again in the CNN. 64 channels, leaky ReLU activations. There's 7 GCM blocks, each with a similar UNet-like architecture employing edge convolutions. I haven't worked with GCMs a lot, but I mean, I definitely am about to get my hands dirty with these, so I'm looking forward to that. But
Have you worked with LSTMs?
I worked with LSTMs badly. I've never had like high success with LSTM, so I'm not convinced that everything I know about LSTM is correct. But I mean, I thought I understood LSTMs, but until I have actual success with them, I'm gonna hold off on saying I understand.
Well, because this is no different than multidimensional LSTM.
Yeah. I can explain LSTMs and it sounds like I understand them, but
Yeah, I know that feeling. I teach classes, right?
Yeah. All right. So, I mean, just to mention again, the GCN ends up predicting something that tells you how to deform the mesh. It's why it's common notation between the papers. Okay, so this is just results, and like the results look decent enough. FreeSurfer fails in some scenarios and succeeds in some scenarios. FreeSurfer's yellow, so I mean, I would say FreeSurfer did better here, honestly.
So I have a question. I actually checked these figures. I don't understand first of all here, FreeSurfer to me seems to work better. And then the other thing is that you should never look at the slice in FreeSurfer, right? It says because the topological stuff can happen because something is there's the slices between slices. So what is the point of this figure in the paper? Are they saying that TopoFit is working better than FreeSurfer?
That's what I was that was my thing. That's why I felt it was so weird that they focus on these things so much, like in the paper. I was like, it seems like you're trying to say it's better, but you don't explicitly want to say it's better.
Well, because you can't prove it.
No, that's what I'm saying. It feels like on the verge of like,
No,
look at this.
In the previous paper, there was a case that the showcases were cases that FreeSurfer failed, right? Those kind of surfaces could not happen for a surface, right? But here the FreeSurfer is actually doing the, if I'm the one who is correcting it, I say, oh, FreeSurfer is better, right? Because it has a darkest spot, so it has to go around. But that other one is worse. So
yeah, I mean,
I would maybe to argue in favor of why they would show this is they're showing what kind of differences their model would make topologically versus FreeSurfer.
yeah,
It's not necessarily a statement of quality, like this is better or worse, but if you're looking for a topological model that makes certain kinds of mistakes or doesn't, or makes certain kind of fitting versus doesn't.
I agree with that, but there's so many of these papers and they all do this and it all feels a little bit on the edge of trying to say it a little bit. Like I agree with you that it is good to show this, right? I'm not saying that it's wrong to show this. But it always feels like a lot of these have these type of figures, like very clear.
yeah. Well, these are also qualitative figures. They're not really quantitative. I mean, it seems like some of them have different strengths than others, but I mean, having worked with the I mean, the amount of it's really difficult to even get in the ballpark of FreeSurfer, to be honest. I mean, like it takes a lot of work to even get here. So like to exclude any of these papers because they have like minor or relatively minor defects in some use cases, have kind of probably slowed down research for other people, because like, I don't think anybody thinks.
Burus Fischel in their workshop, they always say, don't look at one slice. And then he wrote a paper and just showed that one slice. This is what actually bugs me a lot, because still FreeSurfer can fail. You should look at the neighboring slices, right? Because for example, that yellow thing can be a blob, which causes essentially a puncture into the surface, right? But you cannot say that with the surface. It's just with one slice. It's just impossible. So I don't get at why this figure is here at all. It's just because these are surfaces, right? One slice, it's not volume. One slice doesn't mean anything, right? Either of them can be broken by the neighboring slices. So I just don't get how you can use this figure at all, right?
No, it's just a zoom in. Imagine it as a zoom in, and we
I
are
think it
not.
adds value.
Paper is not a perfect media of conveying the information that you're talking about. So they're trying.
I mean,
to
I
show
can see a lot of highly valuable information from this figure. I mean, I can see that it misses this region right here. I mean, they're actually showing you things that they probably want to hide. I mean, and I would think.
Well, but Ashkan is right too. Maybe I mean, it's you both are right in a sense. Like imagine that this is like a channel that's going through in the Z direction, and top of it is missing that channel, sealing it. Like there is some fall there that widens up on both sides, maybe, or maybe it's a puncture, like somebody said. I heard the word, and there is no way to say that.
It's like saying without
From
3D,
slice, you
3D
don't have
information,
a-
it's hard to tell.
Yeah,
Okay. Yeah.
Because in volume, partial volume happened. So, but I don't get it. They talk about it in their workshop a lot, that you shouldn't look at one slice. That is one thing that they always mention. So.
Ashkan, I can refute you sort of by authority. Like those people are from FreeSurfer group. and
I'm just gonna,
They may know what they're talking about, but
Yeah.
it's unfair.
I don't know, since everybody probably wants to leave, or a lot of people leave at 1, and we're trying to like speed this up.
Mhm.
There's a whole other paper to go through, and we have 10 minutes. So,
11.
okay. So basically this lambda term is a hyperparameter that enforces smoothing that they use. This is kind of a weakness, in my opinion, because like while if they seduce the hypertuning correctly, they can get their self-intersections down to like 0.04%. You still have to manually tune that parameter a little bit, and if you don't set it correctly, 5% of the faces are self-intersecting. So that's not a huge weakness, but they're not. It's like it seems like they're allowing below a certain threshold self-intersections, and then you can skip topology correction. I don't know what that. I don't have the domain knowledge to know if that's reasonable, but I mean it probably is. But it seems like if you wanted a perfect surface, you'd still need to do some sort of topology correction.
How does FreeSurfer do topology correction?
I don't know, but it's definitely the most time-consuming part of the process of FreeSurfer, from my understanding.
But TopoFit does or does not do?
Top of it and BoxtoCortex, but don't do it. Do not. Deep CSR does. So they're faster, but they're allowing some percentage of self-intersecting faces.
Because that's not really what TopoFit says in the paper. They do talk about, like that's the reason for the chamfer distance and the loss function, is to keep the shape the same. So it's actually not just the topological properties, it's the whole shape of the object. And they don't say that they don't correct for topological
They
properties.
definitely don't correct.
They absolutely do. That's the point of the chamfer distance. They just don't do post hoc correction.
Yeah, okay. But yeah, that's what everybody in all these papers means by topology correction is post-processing correction of the topology. No.
That's what BoxtoCortex says.
Wait, topology, you mean it's a sphere, right? And it has to stay sphere.
So because they use the chamfer distance, it's not just the topological properties. It's the exact shape of the thing. That's why they're using Euclidean distance. They
Well,
don't
we
actually-
need the shape of the ground truth to reproduce it, right? But it needs to, topology needs to remain a sphere, it cannot have holes.
Well, it doesn't have to be a sphere, right? It can be any kind of shape, it just can't have holes.
A topological sphere, whatever, genus 0 or whatever.
But by correcting for the whole shape using the chamfer distance, that of course corrects for the topological properties. So they're essentially saying like, hey, let's just create a really rigid loss function. And not only that, like by ensuring these, because they use local neighborhood distances, right, in their loss function. So not only are they like, let's make this locally correct, by enforcing the angles and the normals to be the same, they're creating this incredibly rigid loss function, this incredibly rigid surface. And so my deep question is,
Wait, let's wait with deep questions until it's over, because we will stay, but some people will disconnect.
yes.
Why don't we call it? But it will still go on air, I promise.
So basically, the next few sections are conceptually broken down into how they define surface functions on a 3D Euclidean space and how to learn these functions using deep learning. And then second, how to perform surface reconstruction using remote. I mentioned earlier level sets. So basically, their surface is defined as a level set where a function is equal to some constant L. Basically, this is like we've mentioned is probably the first presentation where like the Martian cubes need to like have like some surface like a sign density function to like traverse and like reconstruct the surface.
So
And
some
it's
kind of
following,
a pointer, right?
it's following like wherever this value equals some constant in Martian cubes. So some like level sets can be defined by occupancy grids, as we mentioned before. They can also be defined by a sign density function equal to a constant. You can notice that the sign of the sign density function is defined by this kind of, this occupancy term. This occupancy term actually defines values to be 1 where you're inside of a surface and 0 outside of the surface. So if you're inside of the surface, your sign is one thing, and if you're outside of the surface, your sign is another thing. Points are projected between prediction and the surface here, and that's where you get the distance part, the scalar part. Let's see. So basically, they're trying to define a surface where given a image and a template surface, meaning all of the surfaces that you have in your data set get mapped to the average, and then like also any so basically, given the MRI and the ground truth template, you can predict a scalar value for the sign density function. And the learning objective, this looks a little bit nastier than it is, I think. So like this is a cost function associated with the difference between the predicted value from their network and the ground truth. And I think this is a surface integral, because this is what they define the surface to be. So they're basically trying to find the minimum value of this function. This is a regularization term. Okay, this is where it gets a little bit fun, and we should probably slow down a little bit. So I can either read you a speech or just like we can observe what's on the image, and I think it actually it's a little bit more fun to look at what's on the image. So basically, these are like all conv layers in ReLU according to this, and more convolutions. This is like the encoder portion. It creates this hypercolumn, which gets used as features for the decoder portion. These are all concatenated together from each
Why
layer.
is it cold type of column?
I don't know. I mean, it's just a concatenation of the features from different layers. So they say this is pivotal though, because like if you only get like the last layer, you miss out the fine details of the brain ridges and stuff like this. So that seems to be consistent. And more of the observations of all the papers is that it's good to have features from more than one layer. The decoder portion ends up predicting 4 values. So for like the left and right hemisphere, white and fuel, I think, are inner and outer. And I think that's everything. There's no GCN here. It's all convolution and fully connected networks and things like this.
Oh, wait, so it gets, what is P, X, Y, Z? It's just a coordinate or it is a gray value? Well, it gets as an input, it gets the column and it gets a P as well, a point.
The P is the point. I
Well, is
I
it
think
PT vector?
it seems to be an R3 vector, I would say, but
Oh.
it's like different points in the space.
Oh, so they are learning a field as well. So this F function is defined anywhere.
I think they're learning a sign density function. That's what they're learning.
Well, this F of theta takes a point, it takes some I, what is, so it's like defined at any point, it doesn't have to be on the grid, it can be like you shift X by 0.1% and it will change the value, right?
I don't know. I mean, I know that like
Interesting.
it's basically you're asking the network, what is the value of the sign density function at this point in the MRI? So like, are you inside or outside the surface? And if you're on the surface, you'll be 0. If you're outside the surface, you'll be positive, and you're inside the surface, negative. I might have the signs.
That's what the F is, F of theta.
But there's like a sign and a magnitude. So I would imagine that it's learning, this P value allows it to answer that question for each P that you ask it. So you need the image and you need to be asking it for a specific point. So the marching cube is walking around and basically asking the network, given the image and this particular point, like where am I? And if it's not near the level set where everything's 0, then it's off course. So it's kind of like like imagine like a marching cube would be like trying to draw like a stick figure of like the table, and like being 0 is being on the table, and like if you get too far off the table, like you don't include it in the surface, but like if you're on the table, then it's included in the surface. I don't know if that analogy helped at all, but
Well, that kind of, I understand that, but explaining of the level set or explaining of the sign distance, but then you just scan all the points, or you kind of hone in on the like you converge to where the sign distance is 0 from.
I think I should have answered this on this slide. I may have deleted it, but like they define this omega region that, and they're mapping every I don't know. That's a good question. I don't fully understand it. I
Well,
need to read it more.
Yeah, let's leave questions to just we're
We're
right,
pretty much close to the end.
right at
Like,
times.
like,
One more minute.
I mentally joke with myself that we're cruising altitude by the time we get to this slide, because nothing else is hard, but like basically like affine registration basically means that you're mapping into a similar coordinate space your data set, and implicit surface representation is either the occupancy grids or the sign distance functions, and I'm reasonably confident they're using sign distance functions. Topology correction, as they use the term here, is the post-processing that removes what they call topology defects. I mean, like, I think topology is a pretty broad term. Shape is involved.
No.
Shape's not involved.
No, it's only two things are topologically similar if they're homeomorphic to each other.
Yes.
So there's only certain kind of deformations that make them topologically similar. Hold on.
Yeah.
Let's do this at the end, like the.
Yeah,
We're
let's
close
finish the
enough- we're close
slides.
enough to-
Let's finish
we're
the
close
slides.
enough to the end.
I don't.
Oh, is it
find
the last
explanations
I
more
mean,
than-
if we want this to be an hour long, then we should keep going, but like.
Oh, no, we can continue, like, let's finish the slides and start the discussion.
Okay, so we can come back to this. I'm interested in hearing what you have to say. I just, we need to move on for time.
Yeah, I'm just
Um,
nice to you know.
The, so, like, so basically they're trying to, like, they do some corrections on the topology and then they run the marching cubes algorithm, which basically creates the surface. So I would imagine this is like a sign density function that's been corrected or something like this, and this is like a mesh, but I don't know, I could be wrong. So this result is, they don't have a lot of visual results, and like I said, I skipped a lot of the tables. There's a lot more. I wanted to focus on the methods and less on the results because of time. But this no HC is like if they run their algorithm without the hypercolumn. So they get all of their higher frequency features or whatever from that hypercolumn. So that's pretty cool. And this is just like more examples of like their meshes and the results, but there's a ground truth here. But here, one thing I noticed about this slide is that like the ground truths are red and green, and all the results are much more blue. So it seems like they're on the out. Their predictions always like on the outside of the ground truth a little bit. So it makes it hard to kind of visually compare this to the ground truth. It just, I mean, like it seems like a systematic error of some kind. Like if it was like not biased in some way, you'd see a lot more green and yellow. But anyway, the surfaces look pretty nice. I think it's even though like all the mesh based algorithms that don't do post processing and topology correction, they in their papers claim this method isn't that great, but since everybody's citing it and it seems to go to a fairly high resolution, so like they can do up to 512 cube resolution or whatever. I think it produces solid results in terms of visual quality, but it doesn't produce, it's not beating the time benchmarks. So like you can either try to beat on time or you can beat on quality. I think this paper, this is the same authors that produce, or at least some of the same authors that produce cortical flow, this paper. So whoever does this team has kind of like done all of the stuff that is mentioned in the original paper, where there was like 3 different stages of 3 different types of surface reconstruction, like between this paper and cortical flow, they seem to do both. So, and that's it.
That was part 1 of the series, right? We'll have part 2 in a month or so. So, okay, thanks, William. And now discussions.
Yeah.
You can give the definition of.
Yeah, but we're out of time, so if anyone wants to disconnect or leave, you're welcome to do so. But we'll usually continue the discussion, so that we'll do now.
Simply in geometric space, it's the number of holes in a thing.
Mm-hmm.
If something has a hole in it and something else doesn't, you cannot map these points to this thing with the hole and then map them back.
Mm-hmm.
If it doesn't have a hole, no matter what the shape is, no matter how big it is, because they're continuous space, you can map every point in here to this object and then backwards. Now, the function itself is not necessarily like invertible, but it does have an inverse function. And so that's what matters. And all I know about how FreeSurfer does it is they take the unit sphere and they map points on that unit sphere to the cortex, to their extracted surface. But I don't know a lot of the details.
Right.
They also use the Euler characteristic, which is actually basically, it kind of captures the number of holes in an object.
Okay.
And so they're trying to reduce that number, I think, but I don't know how they do that. I haven't seen any documentation from them about the details of it, just the high level ideas. So I don't know if anybody does know how to do topological correction.
I don't, but I assume that it's probably, there's pretty interesting research papers on it. But it seems like if you could do a deep learning typological correction, you could plug that in as a module in a lot of these. But I don't know if you could do a deep learning topology correction.
There are people who've done that.
Yeah.
I can think of at least 2.5 that attempted something and they kind of work.
Yeah. Yeah, it's probably an NP complete problem. It's not easy to solve well.
How slow is the topological correction? So
I don't know, but like, I just remember reading that, like, that's one of the main time sinks of FreeSurfer, so I assume it's pretty costly.
Okay. So I wonder how much of the 12 hours it actually takes up.
I don't know the specifics. Went out of my mind.
About 8 hours segmentation and all those parts.
Segmentation is 8 hours, and then like topological correction is
Extra 2 maybe. I don't think it's 4. I don't know. But Eloy, from your experience.
I don't know exactly how long, like, it
Yeah,
also
yeah.
depends really on your computer.
I just run recall all and I didn't.
That's what
does it tell
everybody
you
does.
the speed of each function?
Yeah, I didn't.
Probably it logged it somewhere, but who looks at the log? You just look at the free surface and then it's.
Fair enough.
Like, why, like, I mean, for this question, it would be good, but like realistically, why would someone who's like in like a neural lab be like, let me see exactly how long the topology, because they don't care.
Don't you count the stairs when you walk on the staircase? Come on.
You don't check the exact you don't profile every single
You
line.
don't?
Yeah, exactly.
What's wrong with you?
Yeah, exactly. You don't print a file for your file.
Okay, come on. Okay, do we have that? But this is any relevant?
Yeah,
points?
my biggest issue and maybe question, so maybe not issue, with TopoFit is it just seems very strict. It seems like a very stringent loss function because these surfaces can be like the gyrification of each subject can be so wildly different, but to have such a strict loss function, like both on the local distances as well as the normals and angles between the simplest.
Well, but they're comparing to FreeSurfer, and they are from the group that developed FreeSurfer. They trust it, right? So
I don't think they used chamfer distance though in their original topology correction, just based on the timeline of
But-
research.
But camphor is permissive, right? It doesn't like, it allows you to like take that other point and make it closer or something like that.
Yeah, but by adding the regularization term, it's even more stringent, right?
So what's the problem with that? If you trust your ground truth and you want to match it, what's the problem with a strict?
I guess that's actually my issue. I may not trust the ground truth. And I guess we have a
Well, but then we're falling back to what Eloy pointed out and Ashkan, it's like, well, how do you evaluate anything if we know that the teacher is faulty? And we know that still. Like my answer to that from Alex's work of 2016, if teacher is randomly faulty, we don't care. We'll learn over the mistakes. We'll generalize over the mistakes. If teacher is systematically faulty, we will learn the mistakes.
if the teacher is from their built-in topological correction, it's gonna have the same artifact.
Yeah, I was gonna say, it is systematically mistaken, obviously, in FreeSurfer, because it is very step-by-step deterministic. Like it's a,
Well, the randomness comes from differences in subjects.
No,
the
right,
collection.
but I mean more like, I think there's certain things that, there's probably part of it is random, but I think there are obviously a lot of things that are pretty like just systematic because of the way they had to make, like the unit sphere assumption, for example. That's, one way of doing it, that they're doing it, and that obviously can lead to some type of artifacts, like those assumptions they can lead to certain artifacts.
I want to say something. Like, I think the one thing that I would be awesome, and I have no idea how to do this, but is to make this like unsupervised and not require FreeSurfer or something, self-supervised or something. I mean, like, could you get rid of segmentation and replace it with an autoencoder? And I don't know how you would replace the mesh portion, because you need the ground truth mesh, but like, I don't know how you would make this unsupervised, but since everybody's trying to replace FreeSurfer, like everybody's dependent on FreeSurfer. Does anybody know of any papers that might indicate how you could make this?
Well, the question is, you need the mesh to do something unsupervised. If
So
you're trying to like reconstruct it again.
There are different ways to build a mesh. And I had to, FreeSurfer's documents are not very clear on how they construct the mesh. So I had to dig through the code, and from what I gathered, they basically just take the image and treat each voxel as a point and then build the simplexes from those points. So it's actually, they're actually non-equilateral triangles, which
They don't have to be.
But
It's a regular mesh, triangular mesh,
They don't-
used everywhere.
they don't have to be anything. It's just a fun thing, I think.
Well, they have to be equilateral, right?
No, they don't have to, well, they're not.
Well, you start with icosahedron, right, or whatever you, and
So they treat each voxel in the image as a vertex. And they build the simplexes based on those. So if you have,
FreeSurfer starts with segmentation though, it's on the surface, at least on the.
no, but to build so maybe I'm mixing terms, but to build the mesh over the surface, to extract the surface. That mesh,
But you start with segmentation, you know the surface voxels.
you mean white matter, gray matter?
Yeah, you know the
Oh,
surface voxels already, you know the voxels on the surface, that you know. You don't start with all of the voxels.
Right, you remove the whatever.
You use the for all qualifier, which is a no-no.
You use recon all and it does it.
It's not for all, it's just for the surface voxel.
Yeah, oh, yeah, sorry, of course. But it doesn't matter that they're not equilateral triangles. But there are lots of other ways to build this mesh, and I am curious if they've ever tried anything. If they've tried blowing it up to larger spheres, if they've tried neural networks, if they've tried anything else to create the mesh over the surface.
I think I'm not following what does it mean to create a mesh. Like I can take a sphere and tessellate it into triangles using.
Yes, the tessellation is what I'm referring to.
Yeah, and I can give you a spherical mesh.
Yeah.
And a brain scan T1 image, and like again map that image to the surface of that brain. So you're saying that tessellation of a sphere, all the tessellation of a sphere, right, is the key. That are you saying?
Are you sure are you saying they blow up the cortex and then to a sphere
That's what I thought too.
and then tessellate over that?
Yeah, that's what I thought too.
I'm saying they're taking icosahedron and doing subdivision of icosahedron by blowing up to the same radius as they go, and they get the tessellation of the sphere.
Yeah, that's what I thought.
It's kind of uniformly covered, but when I was in Los Alamos and I was talking to people there I needed tessellation and an algorithm that uniformly puts the points on the sphere, and then I can tessellate using Voronoi and Delaunay triangulation and all that stuff. But they were like, no, those algorithms that do perfect or whatever close to perfect are classified, because you really need them to model the explosions and stuff. But because I was thinking, why hasn't anyone modeled those points as charges? And they repel, and now we have uniformly covered with charge and blah blah blah. Well, there must be code somewhere around Los Alamos for that.
Well, Los Alamos, yeah, I was gonna say,
Yeah,
that's the perfect
and
place
they
to
were
look
like-
for that type of stuff.
They didn't give you the code.
Yeah, I think that's also what I thought, they kind of like blow it up like slowly, and then they are like, okay, now it's a sphere, and now we're gonna like make the tessellation.
Still recording. Yeah, I know, because we're still discussing. Well, thanks everyone. We're only 10 minutes over the grace period, and next time it's my turn to talk about what was I going to talk about? Conformal predictions. It's about uncertain sequence quantification and anything.
Well, in this case, maybe.
And yeah, I mean, let's see.